All right, everybody, it's 1:03. It's a good time to start the lecture. So welcome to the third lecture of the Statistical Foundation for Reinforcement Learning. Um, yeah, I think we now have almost everybody. Let's get the lecture started. Um, yeah, so actually before I start the lecture, I wanted to say a few logistical things. So first of all, I ask you guys for forgiveness if when or whenever I won't be able to get you the homeworks or graded homeworks, or things that I promised you in the lecture like on time according to the same timeline. So I realized that I promised you that I will send you a list of project ideas before the end of last week, which I didn't manage to do. So just notice that in this course, I'm running this course all by myself. I do not have any TA support, and some of my students in my group, they are helping me on a voluntary basis. So I get some scattered help, but like really, the course won't be as organized as some of the other the undergraduate level courses that you guys have taken before. So I ask your forgiveness on that. On the other hand, I also try to maximize the flexibility in the course. So if you have special considerations for submitting homework for things that you need to take your time on for working on a project that's slightly different from what we're doing in this course, and that's perfectly fine. Just reach out and talk to me. Okay. Um, okay. So today's lecture 3 for reinforcement learning. We're gonna be continuing the discussion on Markov decision processes. And today we're going to be talking about how do we learn Markov decision processes with a generative model, which will be a setting that's closely related to reinforcement learning. Okay, so as usual, all the good materials are worth covering twice. I'm gonna give you a quick recap of the last lecture on what we talked about, what we now know about Markov decision processes. So to begin, we decided to focus on the infinite horizon discounted Markov decision processes. By now, these parameterizations of the MDP should be clear to you. So we have the transition kernel, the expected reward function, and for simplicity, often we assume that the reward function is given to us. Meanwhile, like both the transition kernels and reward function can be estimated from data. And then there's an initial state distribution, mu 0. There's also discounting factor gamma that's between 0 and 1, right? So all these together with the state space and action space specifies the infinite horizon discounted, gamma discounted Markov decision process. And to evaluate the performance of a particular policy, we for any policy we can write the reward function, the value v value function, and q value function corresponding to those policies, and the reward function is the immediate reward that you receive, the expected immediate reward that you receive at state s when you take action according to policy pi. Right, so that's the immediate reward. And if the policy is stationary, then this index 1 doesn't really matter. You can replace this index 1 with arbitrary number. And yeah, but by the way, so the notation wise, I'm using the capital letter SA R as say as ST, AT, RT to denote the sequence of random variables that you obtain by playing policy in this Markov decision process, right? So these are random variables. I'm overloading the notation sometimes because these are simultaneously the random variable, state action, reward, state action, reward. But I'm also using S to denote the cardinality of the state space S, and A and capital letter A to denote the cardinality of the action space A. So sometimes what they mean are clear from context. Just like I'm doing this to avoid a lot of superscript and subscript, which we already have a lot, and notation clarity, and to avoid clutter. So sometimes we're like overloading notations. All right. So the state value function says that you start with state S, and subsequently you take all your actions according to policy pi, right? And state action value function, also known as Q function, says that you start at state S, you take action A, and subsequently after you transition to the next state, and then you take further actions, and everything else will be chosen according to policy pi. Right. So these are the first principle definitions of the state of the V function and Q function. Meanwhile, we talked about in the last lecture we've established that for this MDP, it suffices to consider just stationary policies, and for stationary policies, they satisfy the so-called Bellman consistency, or they give rise to a family of linear equations describing the relationships about describing the recursive relationships of the value functions. So for such stationary policies, they are equivalent definitions of these V functions and Q functions that you can prove from first principle directly by this argument of shifting the change of variable by defining T tilde to be T minus 1, and then shifting the entire Markov decision processes to one step into the future. And since everything is stationary, as long as you're starting at state S, it doesn't matter what the actual index is, and therefore you can write the right-hand side and use this V function again on the right-hand side. Okay, so these are matrix. These are like linear system of equations. So it looks like that plus a matrix multiplying with V. So this is what these equations look like. So I'm like using the superscript pi to denote that this transition is a state transition induced by taking action according to policy pi, right? So this is our S by S. On the other hand, this is our SA by S, right? And in the third Bellman equation related to Q function, this matrix is our SA by SA, right? So that was why I added a tilde here from the last lecture to indicate that this is a different way of constructing the state action transition matrix under policy pi. Okay. And on the flip side, there are these notions called occupancy measures, which measures the expected expected number of times that your agent will visit particular state action pairs throughout the entire infinite horizon. And it is discounted. So the number of times is also discounted by gamma to the power of t when t is t minus 1 when t is a step into the future, right? So this is called the discounted. This new functions discounted occupancy measure. So the discounted occupancy measures also satisfy the Bellman equations, which looks like the following. So we derived this from first principle in the first two lectures. So this one is on the order of SA, because this is state action occupancy measure, and when we add a tilde, then we get this state occupancy. This is a state occupancy measure because this mu is the initial state distribution. So this is in R of S, and we add tilde, we get a state action occupancy measure, which measures exactly the same thing. So except that now we so SA, you can more or less deal with it as if we are dealing with probability distributions, though this is a general measure, not a probability distribution. You can you can construct the state action occupancy measure by simply multiplying that with the corresponding policy to construct something that resembles a joint distribution of S and A. Okay, so what are nice about these Bellman equations is that they're linear system of equations, and we can work out the closed form solutions for all these quantities. For instance, V pi, we can write it as identity matrix minus gamma p pi inverse r pi. Okay, and q pi is equal to identity minus gamma p pi theta inverse and r, right? And nu pi, the state occupancy measure is identity minus gamma p pi transpose inverse mu, where this mu is the initial state distribution, and the state action occupancy measure is equal to I minus gamma p pi transpose inverse and mu pi, and this mu pi is equal to mu pi SA is equal to mu pi S multiply with pi A given S. Yeah, so it's the same as above. You can just, yeah, this one is the actual joint distribution of state action pairs on the policy pi, right? So you can see this nice symmetry between the value function and the occupancy measures, and these are not surprising, as we talked about in the last lecture, that there is a linear programming formulation for solving Markov decision processes. Okay, so the optimal value function, V star is the optimal solution of the primal linear program. On the other hand, when you use a standard like dual ILP, when you derive the standard dual ILP either through the canonical formula or applying the or just applying the Finchel duality or Lagrange duality directly to derive this by adding this Lagrange multipliers nu, and then you derive this dual LP, and the optimal state action occupancy measure under the optimal policy pi star is the optimal solution to the dual LP. Okay, so and by strong duality, we know that the minimizer of the primal LP is the same as the maximizer of the dual LP. They have exactly the same value. So now let's look closely into what this means. So let's say that for for any pi, like for any pi, for fixed policy pi, let's say that there is a state action occupancy measure nu pi SA, right? Clearly, like what this is just a Bellman equation that we talked about in the previous slide, right? Clearly, this satisfies the Bellman equations of occupancy measure. Therefore, this is feasible. For the dual LP, right? Let's say that the dual LP, it looks like that, and this is the optimal objective function value. This is the optimal objective function value that you get. Then whenever you choose a pi that is suboptimal, then let's say you're here. But it is a feasible solution, and you can calculate this its value function through the objective function itself. Okay, so dual LP is really just the maximizing the cumulative reward through the particular decomposition of the cumulative reward via the occupancy measure and the reward function. Okay, so now let's take a closer look at the primal LP. What does primal LP do? So suppose we fix pi, and v pi. So let's say that this is a state value function for policy pi, right? So then what is the objective function? The objective function is v pi inner product with mu, right? So this is equal to v pi of mu according to our notation. So this is also the value of policy pi. This is also the value of policy pi, right? So it should be exactly the same as this value, but wait a moment. Wait a moment. This is like we know that by strong duality that the optimal primal LP cannot be lower than this dashed line. It cannot be lower than this dashed line, right? But now the objective function value, suppose we plug in this v pi is actually the same as this point, right? So this by contradiction, it implies that this v pi function is not a feasible solution to the primal LP. Why is it the case? Because the primal LP actually wants the actually wants this inequality to hold for all action and state pairs, which is a property that is only satisfied for the optimal value function, right? So primal LP is trying to find upper bounds of the optimal value functions, and then you're trying to minimize the upper bound as much as possible until you reach the point where your v argument v is actually the optimal value function. For all other suboptimal policies, if you substitute v into the primal LP, then you get something that's infeasible, as we've shown just now. Okay, so I hope this revisit of the primal and dual perspective of Markov decision processes help you to understand like what's really going on here. So primal LP is minimizing an upper bound of the v star function, the optimal value function, and dual LP is optimizing over the policy by pushing up the value of that policy as much as possible, right? So the dual LP is in some sense policy optimization, and primal LP is in some sense like in this sense, I think the dual LP like is more natural, and the primal LP, not surprisingly, is a dual of the dual. All right, so now change the color of the pen to this again. Okay, so the key focus of the last lecture was to understand how we can derive the optimal policy given derive the optimal policy like iteratively, or use other means by solving that LP, and about the computational properties of these algorithms to solve the so-called planning problems for Markov decision processes. And at the heart of these this algorithm is a Bellman optimality equation, right? So the Bellman optimality equation does follow. It's a nonlinear relationships thanks to this max of A. So we can also write it as a Q star is equal to I guess R. Yeah, let's ignore that. SA and plus gamma and V star S prime, yeah, gamma, and then I guess summation over P S prime S A over S prime, right? And what is V star? V star is equal to the max of Q star S A over A, right? So pi pi star s. So the deterministic and stationary policy that achieves the optimal that achieves the optimality for the Markov decision processes is the argmax of Q star function. So that's the conclusion based on the Bellman optimality equation. And the objective function value of this maximization is a V star function. So if we plug this into here, we get this we get this nice looking both left hand side and right hand side that both depends on Q. So we'll get gamma gamma and this P matrix and multiply with max A and Q star S prime A prime. Okay, so that's the kind of Bellman optimality equation that depends only on Q star, right? So and also we call this right hand side the Bellman we call the right hand side the Bellman operator. So the Bellman operator applying to Q star, right? So this is a nonlinear operator that takes this max over A and multiply with a linear transformation and then add the immediate reward. So that's what we call the Bellman operator. And one key result that we showed in a last lecture was that the Bellman operator is a gamma contraction, which means that when we apply this Bellman operator to two arbitrary vectors of the size SA, then in terms of the L infinity norm, it shrink the distance between the two vectors by a factor of gamma. So this implied that if we repeatedly apply this Bellman operator, then we'll get a geometric sequence that converges to 0 in L infinity norm, and that gives rise to the convergence rate analysis of the value iterations. Okay, so I hope this still makes sense to you. So we'll be using this gamma contraction idea again in today's lecture for a different purpose. All right, so the ending notes of the last lecture was the computational complexity of the theory algorithms that we talked about, the value iteration, policy iteration, and LP algorithms. So again, the value iteration is about repeatedly simulating the Bellman optimality equation and recursively calling it until it converges. And the policy iteration is slightly simpler, which involves two steps. So repeat, the first step is the policy evaluation. Of pi t, and then update policy improvement by choosing pi t plus 1 equals to R max Q of pi t, right? So for policy evaluation, we can solve a linear solve Bellman equation, right? By solving a linear system of equations using any means that you like. It involves inverting a matrix. And since for a fixed policy, then for a fixed policy, this pi t the Bellman equation is linear, so you can easily solve it. So there are distinct properties of value iterations and policy iteration, and also the more generic linear programming algorithms, the interior point method that you can use to solve the MDP by finding the policy. So we can see that all of them depends polynomially on the size of the state and the size of the action space. Okay, so there are some more subtle discussions about whether these algorithms are polynomial time, which depends on the smallest machine precision. So you should really think about this as you should really think about this LP R gamma term to be something like log 1 over epsilon term. You should think about it log 1 over epsilon term, and all these computations are stated in big O notation. Right, so some numerical constant in front of it, say 10 or 1,000, they are ignored. we're thinking about really large problems and consider only the dependence on the size of the input. Okay, so surprisingly, the policy iteration approach, even though it's just a little bit different from value iteration, you can actually derive bounds that's independent to this small approximation constant epsilon. Meanwhile, the LP algorithms, they are known to be strongly polynomial. So by higher order dependence on state space and action space cardinalities, and you can come up with bounds that output the exactly optimal policy without any epsilon that's strictly larger than 0. Okay, so one thing that I wanted to mention is that certain polynomial dependence on state and actions are really required because we need this even to store the Q star function, right? Storing policy you can get away with S log A, but in order to learn, in order to figure out what the actual Q star function is, you have to at least go over each action for each state again to figure out what is a maximizer, right? So after that you can store the policy with S log 2 of A, but arguably the linear in S and linear in A is a lower bound for computing the optimal policy. Okay, so in this lecture we'll see whether we can get close to this lower bound and whether we can improve the computational complexity over these methods, value iteration and policy iterations and so on. Okay. So let's set up the problem a little bit more. So the key idea is the introduction of randomness. Okay, suppose we allow like random access to the transition kernel. So maybe suppose we can sample from the transition kernel rather than like numerically representing everything about the transition kernel in the RAM. Can we further improve the computational complexity? So maybe at the cost of a slightly worse dependence on this epsilon parameter. So the motivation is really that notice that the best performance in all these existing algorithms, in all these like exact algorithms, they depend at least quadratically in the state space. And in practice, we are interested in solving really large Markov decision processes. So just to give you some ideas of how large the state spaces are. So if we consider some of the games that artificial intelligence had previously conquered, so in backgammon and chess and Go, like even the smallest game of them all, backgammon, the state space is on the order of 10 to the power of 20, right? So for the game of Go, it's really like linear in the state space is unacceptable, let alone quadratic dependence in the state space. So of course these are degenerate examples because in these cases the state transitions are often quite sparse. When you put a tile here, then there are no randomness, and then you can transition only to one particular state deterministically. But in general, when we are dealing with Markov decision processes, there are stochastic transitions, and we need to somehow represent the full probability distribution from one state to the next, which gives rise to S square A dependence. So as a matter of fact, the transition kernel itself like needs this many parameters to even describe it, right? So and the value iteration, policy iteration, they require applying the transition kernel as a matrix, as a linear operator to some vector, and matrix vector multiplication would take the size proportional to the size of the matrix. Okay, so the idea of introducing randomness is to say, what if we can do a stochastic approximation of such application, right? So even though this one is SA times S, but maybe we can get away with finding an approximate solution where this P is replaced by something that's sparse. And this something sparse can have a substantially smaller number of non-zero elements, which would allow us to reduce this S-squared dependence at the cost of being approximate. Okay, so from the time being, let's say that we can sample this transition in O1. Okay, and this is a well-studied setting called the Markov decision processes with a generative model, or reinforcement learning with a simulator or with a generative model, where you can sample in O1 time, like for any given state and action, you can sample sample a random transition into the next state. Okay, so when is this model meaningful? So why are we studying this? So so first of all, sometimes we do have good simulators. So in environments such as the games that we discussed just now, so we know this similarly exactly. And let's say in backgammon, so you need to toast dice to determine the next state. Then we can toast the dice at any given like starting board board position. And similarly, in robotic simulation, sometimes we have a good dynamical system model for the robots. We have all these ordinary differential equations to describe the torque that we apply to each joint and how the body parts of the robot is gonna be moving. So sometimes doing this simulation are significantly less costly than actually running this robot in the real life and risking breaking them, right? So this is the case, say in RoboCup. So there's this yearly competition in robotic soccer, and it's really fun to watch. So a lot of those policies that they learn how to control those robots and how to coordinate multiple agents to beat their opponents is through learning with a good simulator. Okay, so in science, say in material discovery, this is also the case that we could sometimes have a good underlying physical or chemical model that we can generate samples from a state transition given any state transition. So this is not a greatest model to study if the situation of applying reinforcement learning of Markov decision processes are those where you do not actually have a good understanding of the world. If your simulator is just a very crude approximation, then using the generative model to learn will end up giving you very suboptimal policies. Yeah, so there's a so there's a question in the chat, which is interesting. So the question says that, is this approach used to make an agent learn without making lots of costly computations? Yes. So if we have a simulator, then yes, sampling from the simulator might be easier than writing down the probability distributions and applying the exact transition of that probability distribution directly. So that's one aspect of it. On the other hand, you can also think about this as a simplified version of a reinforcement learning. When you do not actually know the state transition, now all you have to do is to all you can do is to interact with the world. So each time you interact with the world, then you get a transition, right? You get a sample from that transition. So this gets us like one step closer to the reinforcement learning setting. The key difference is that in the generative model setting, you can specify what these state action pairs are, right? Whereas in the full-fledged reinforcement learning, you have to plan a sequence of strategic actions in order to get you to this particular state, right? So exploration is completely ignored in the setting of generative model, but that also makes this a very clean model for us to understand how many samples do we need to actually learn a good policy. Okay, so of course, when the simulator itself is very costly, so this is often the case in science simulations. So there is a trade-off between the extent to which it is approximate and the extent to which the simulator is computationally tractable, then there are really trade-offs that you have to think about, and they're actually interesting question to ask, whether you can start off with a very crude approximation so your simulator can stop early, and then in later phases, as you get closer to the optimal policy, maybe you want to use a more fine-grained approximation and spend more time on generating high quantity samples, right? So there are a lot to be done here, specifically in terms of RL for science. Okay, so the key question that we are going to be asking is how many generative model oracles do we need to call in order to how many times do we need to call this generative model in order to obtain an optimal policy? Okay, so you can so I think this slide also addresses your question on whether this is a computational, where we're calculating the computational complexity or the sample complexity. So they're closely related. So if we assume that it is order 1 time to draw a sample to call this oracle, then the number of times we call this oracle will likely to be us running running this oracle as a computational trick and to do better than say S squared times A polylog. On the other hand, if we think about this to be a simplified version of reinforcement learning without worrying about the exploration, then this is more closely related to sample complexity. So how many times that we have to interact with the world and collect data, and how many data points that do we need in order for us to learn a policy that's sufficiently close to the optimal policy. Okay, so this is a goal of the setting. And then the next natural question is that now that we have a simulator, so there are a million different ways that we can make use of this simulator. And so in particular, this simulator says that we can choose any state action pairs. So how are we going to choose it? Should we choose it as an adaptive sequence? We first choose SA to be this. After we see this S prime, then we can decide on the next SNA. So that might have some interesting properties with such an adaptivity. But for now, we'll just use the most straightforward way of using the simulator. So we'll sampling n full rounds in the round robin fashion. We'll go over each state action pair in state space, product action space. We'll go over each state action pairs once in each round. So in total, we get total number of oracle calls is n times the cardinality of S times cardinality of A. Okay, so this is the total number of times that we wanted to call. And then we really care about how large this n is. Suppose n is on the same order as S, then we are back to the value iteration in the sense that we're not improving the computational complexity at all. So recall that in policy iteration, we get S squared A log 1 over epsilon over 1 minus gamma, right? 1 minus gamma square. Inside the log, the power doesn't really matter. So that's a computational complexity for value iteration. So if n is larger than S, then we recover S squared times A, and like this randomization doesn't really help us. Okay, so far we consider this approach of collecting data and running the simulator. So there are better ways, obviously, but for now we'll focus on this one, mostly because in the worst case, this is without loss of generality. So in the worst case, there are no other ways that does substantially better than this seemingly naive approach of just going around all state action pairs. Okay, so how we're going to be using these samples that we collect. So the idea is to simply plug in, right? So this is a maximum likelihood estimator for the transition kernel. So for every state action pair, we can estimate the probability of transition into S prime by counting the number of times S prime SA triplets appear in the entire data sets. Okay, so you can alternatively write it as a random variable. So let's say that for each SA we collect, we sample IID S prime 1, SA, S prime 2, SA to S prime N SA, right? So these are the samples that you got from the simulator. And then using this indicator vector, you can write this counting to be the summation of this Bernoulli random variable. Okay, and each individual random variable is drawn from Bernoulli with probability with probability P of S prime S A. Okay, so in total, as we talked about earlier, so there are S squared times A parameters in P. Okay, and what we want is that we want N to be substantially smaller than S. So this means that we cannot possibly, with N smaller than substantially smaller than S, we cannot possibly get a good estimate for this P for this P matrix. So a lot of the elements of P hat will be 0 for many for many S prime. Yeah, so let's say that we're only getting N SA samples, and each samples contribute to at most one entry, right? So when we do not see anything, this count will be 0. Therefore, like this matrix will be sparse, right? So the key question of interest is can we still obtain near optimal policies even if we're not estimating this transition kernel accurately in L infinity norm? So that is a question that you should keep in mind for the remainder of the lecture. Okay, in any time that if you have any questions, just either unmute yourself and speak up or type into the chat. So when I see your questions in the chat, I will just respond to them. And also, if I'm going over this too slowly and you find it boring, or I'm going over it too quickly, you should also let me know, and I'll adjust the pace. Okay, so in the remainder of today's lecture, we're going to be talking about a couple of approaches of analyzing how large this N is as a function of epsilon, or bounding epsilon as a function of N, and as N goes to infinity, this epsilon should go to 0. Okay, so we'll talk about some of the key results in Markov decision processes, such as the simulation lemma, and we will review some of the statistical tools that we need to analyze the sample complexity. So the goal of this lecture are never really for the sake of learning Markov decision processes, learning reinforcement learning. I also wanted to teach you things that you can apply more generally. So to analyze randomized algorithms, to analyze the statistical convergence, and so on with finite sample bounds. So these tools, Hofstein's inequality, Bernstein inequality, and McDiarmid's inequality, they're some of the most popular and most useful hammers that you could possibly imagine in the statistical machine learning area, right? So I think every 6-7 papers out of 10 papers, you see papers using these inequalities. Okay, and then we will apply these tools to derive 2 different sample complexity bounds. Yeah, nice question, Diraj. Yes, so for now we assume the reward is bounded. So sorry, the reward is known. So wait. So let me patch that. So I forgot to mention it. Wait, maybe I have another slide. That's for. yeah, so yeah, maybe let me just write it down now. So we're trying to make use of this empirical estimate of P by coming up with an approximate MDP, state and action space, and then state transition hat, and reward we assume that it is exact, and mu initial state and discounting factor, right? So it is also reasonable to say that we also need to estimate the reward, right? But that is less of an issue. I intend to leave it as part of your homework one. All right, so for now we assume that this reward is shared knowledge. Now so the idea of the model-based approach is really to first estimate, like I wrote previously, first to estimate the p hat and then come up with the approximate MDP as a p hat r mu gamma, and then with this approximate MDP, then we can run the either value iteration or policy iteration on this. Okay, and the idea of analyzing the performance of such, so let's say that we run value iteration on this m hat, and what this gives us is a policy pi star, right? So what this gives us is the optimum policy corresponding to pi star, and pi star is the arg max of the q hat star, and q hat star is a optimal state action value functions of q hat star is the optimal value function of m hat. Okay, so similarly, q star is optimal for m, for the original MDP. Okay, so the idea that we're going to be using is to use a standard trick called uniform convergence. So let's start with what we want to begin with. So we want to bound the value of v star. So this is the same as an optimal value function minus v of pi hat star, right? So this is what we want. And what can we and what can we do? So we actually want to bound this for every state and action. So maybe let's write state here. So let's now add and subtract. I'll drop this S for clarity, and all these bounds can be interpreted as pointwise as vectors. I'm gonna subtract v hat pi star, v hat pi star. Okay, I'm just gonna also subtract v hat pi hat star plus v hat pi hat star and minus v pi hat star. Okay, I'm basically just adding and removing the same thing. So now let's group this suboptimality. So the goal is to bound this. We want to bound this by epsilon, right? So the goal. So now like we need to like look at the three terms. So first of all, the one in the middle is strictly smaller or equal to 0. Why is that? So this is because pi hat star is a maximizer of v hat q hat pointwise, right? So therefore this is really the v hat star function. Therefore it is better than any other policies. So that's why this is smaller than 0. And for these two, we need something called a uniform convergence. So if we can come up with bound of the following form, if we can bound the soup over all possible policies, such that v hat pi minus v pi is smaller than epsilon, right? So this is a kind of uniform convergence bound that we're going to be proving and leveraging to get this suboptimality bound. So notice that when we when we take soup, then this bound applies to any chosen policy, right? So we can choose this policy to be pi star, which gives us this term smaller than epsilon. We can also choose this policy pi to be pi hat star, right? And this gives us something that's smaller than epsilon. So overall, this gives me a bound of 2 epsilon. Okay, so this reduces the problem for using n samples and to establish that this sets such uniform convergence bound. Okay, so this is a standard trick that's being used in machine learning a lot. So now let's before we go to the statistical analysis, let's maybe compute the computational complexity of end-to-end, because ultimately there's also this this value iteration procedure that's going on, right? There's also this value iteration. So let's divide the computational complexity into 2 parts. In the first part, we'll work on the approximate transition kernel. So this is about constructing p hat, right? So recall that for each SA pair, then we sample n copy, right? So the time complexity will be proportional to n times SA, right? And the space complexity will be the space of p hat. So this would be the number of non-zeros at SA pair multiply with, so I guess average number of non-zeros times S and A. And I guess it is the mean of, this is smaller than N SA obviously, but it is also smaller than S square of A. So it's a minimum of these two quantities, right? So now, so how about value iteration? So in value iteration, it takes this many iterations. And so this is the number of iterations. And each iteration requires us to apply this approximate transition kernel, which would be which would be n as NSA, the minimum of NSA and S square A, right? So the overall computational complexity is fine because because to construct the approximate kernel, you only need n. So as long as n is smaller than s, then we get an improvement over the standard method, maybe at a cost of epsilon. Okay, so let's try the first attempt to analyzing the sample complexity, right? So yeah, what this shows is that it really suffices to work out what n is if we want to get the epsilon approximate optimal policy, right? To work out n as a function of epsilon. Okay, so let's try working out the first version of it. So our first attempt will be to use a classical result called a simulation lemma, which decomposes the difference between Q function of pi on the original MDP and the approximate Q hat function of the approximate MDP for the same policy. Okay, so it is a identity and it is easy to prove. So let's see how the simulation lemma works. So first of all, like we are applying the closed form solution that we just reviewed of the Q function, right? So this is applying the closed form solution of Q pi and the closed form solution of Q hat pi under the 2 MDPs. Okay, now the second line. So notice that this one is just Q pi, And this one, I can using the invertibility of these matrices, I can first multiply I minus gamma p pi and multiply I minus gamma p pi inverse R, right? So now this becomes Q pi as well. Okay, and then then I can do the same trick here by adding I minus gamma p hat pi inverse and yeah, this and I minus gamma p hat pi inverse, right? So now by grouping these two together, I can extract the common, I can extract the common Q pi function here. Sorry, common Q pi function here, and extract the leading term here, and that gives me the leading term here. So what remains is the difference between this and that, and that's how I get this term in the middle. Okay, I hope that's clear. So the identity matrix are canceled with each other. I'm extracting out this gamma, and in the middle I get this p pi minus p hat pi, and notice that Q pi S A is equal to V pi S multiplied with pi S pi A given S. So by grouping this pi with a transition, so by yeah, by grouping this pi by with this transition that we can get rid of the pi dependence on these transition kernels. Then we will yeah, yeah, I see by yeah, this is by collecting sorry. So p pi S prime A prime S A. So this is the same as p S prime S A multiplied with pi A prime A prime S prime. Yeah. So by combining this with a Q pi S prime A prime and then add them up, then you can replace this Q pi with this V pi and get rid of this quantity in P minus P hat. Okay, so that proves the simulation lemma. So let me parse the simulation lemma for you. So why is it useful? So it essentially changes the differences of the value evaluation of a policy on the true MDP on the simulated MDP, right? So this is a simulated MDP Q function, and replace that with the with a difference of the approximation to the transition kernel itself. Okay, so this offers us an opportunity to further bound these differences in transition kernel and then proceed with the argument. Okay, so let's see how we proceed. So we basically take the L infinity norm on both sides, and well, and then I'll show you how this how the first inequality works. This is something that we have actually proven last time. This is something that we've proven last time when we proved the invertibility of such I minus gamma p matrix when p is an arbitrary transpose of a transition kernel. So let us prove this again. So why is 1 true? Why is this inequality true? So essentially what we need to prove is that I minus gamma p hat pi inverse times x L infinity norm is smaller than 1 minus gamma x infinity, right? So this is what we need to prove. Let's do a change of variable and then call this whole thing y. Okay, so then this is equivalent to proving 1 minus gamma I minus gamma p hat multiply with y is larger than I guess 1 minus gamma x, right? And how do we prove this? So we'll go by go by the triangular inequality. Yeah, this is the same thing that we used before. We use a triangular inequality to lower bound this by and minus gamma p hat pi and y L infinity, right? And then using the property of this matrix has L infinity norm operator norm bounded by 1, then we can further lower bound this by y star y L infinity 1 minus gamma. Then we can divide then we can divide both sides by this is y. We can divide both sides by 1 minus gamma, and then it gives us what we want. Okay, so what it's saying is that we can get rid of this matrix and replace that with 1 minus gamma here. Now we got something that's a lot cleaner. And then this is still a matrix vector multiplication. Let's look at every coordinate separately. We'll look at every coordinate as A separately, and then this becomes I guess max of SA and P SA minus P hat dot SA multiply with inner product with V pi absolute value, right? So this is what this L infinity norm mean by its definition, and then we can apply Holder's inequality. So hopefully you have done the homework 0, in which case you are asked to derive the Holder's inequality with L1 and L infinity split. So this is exactly what we are doing here. We're taking the L infinity norm of V pi. We're taking the L1 norm of this difference. Okay, so how large is this? So by discounting and the bounded reward between 0 and 1, we know that the L infinity norm of V pi is always smaller than 1 over 1 minus gamma. So that's why we now have a factor of 2 here. And it remains to bound the L infinity L1 norm bound of the standard probability distribution. So there's a question, did we omit gamma intentionally in the first line of the proof? Are you talking about this gamma?
Yes.
Yeah, we didn't omit it. The gamma is basically taken. We didn't omit it. The gamma is extracted outside the L infinity norm, right? Because any norms are linear to scalar multiplication, so we extract it out, and we were just proving like a more general lemma of the operator norm of this matrix inverse.
Oh, okay. Thank you.
Yeah. Okay, so now one key observation is the right-hand side is a quantity of stochastic approximation that doesn't depend on the policy at all. So if we come up with high probability bound of this term, then that will imply that the result will hold simultaneously for all policy. hence we can essentially add sup over pi here, which gives us what we want from the previous previous page. Well, yeah, this kind of bound. Okay, so now let's move on to bounding the convergence of probability distributions. Yeah, so I'm running a little bit behind on my schedule, so we'll skip the break today. So that we it's more likely for us to finish on time. Okay, so now we move to the second part of the lecture, which is statistics. So statistics is hyper important, obviously, and well, luckily, so all you need to know, at least on the intuition, the intuition of statistics in one slide is just two theorems. So statistics deals with samples that you are drawing from some probability distribution. So without specifying what this probability distribution is, then statistics tells you that under like very weak conditions, then there's something called law of large number, which says that average of these IID samples of these independent samples will converge to their mean, will converge to their expected value. Okay, so this is often converges almost surely on the like very weak regularity condition as n goes to infinity. There's also some something that tells you how quickly it converges to the mean, right? So the mean that the average that converges to the mean at a rate of 1 over square root of n. As n goes to infinity. Moreover, it actually converges to a standard converges to a normal distribution. So that's called the central limit theorem. It's a universality result. It doesn't like make much assumptions about this probability distribution, but as long as you have a large sample, then it converges in distribution. So this is convergence in law, convergence in distribution, sometimes denoted with this squiggly arrow that's pointing towards this distribution. Okay, so it tells you that the rate of convergence is square root of 1 over n, right? So this is all you need to know about statistics, at least on the intuition level. Of course, this is a graduate level course, and we want to do analysis using statistics, so we need more hammers that allows us to formalize this idea of statistical convergence and the rate of convergence, similar to central limit theorems. Okay, so let's introduce a set of concentration inequalities that we need. So the first hammer that we need is a so-called Hofstein's inequality. This is also from homework 0. So if you have done homework 0, you should have the level of familiarity with this. Let's say that, so the statement says that you have n independent samples that do not need to be identically distributed, and they're support bounded, which says that the probability of xi is bounded by ai, is bounded between ai and bi with probability 1, right? So modular some not measurable events, probability 0 events, then xi is bounded. Right. So when we have this, then we can bound the sum of these n random variables from its expectation by something that goes to 0 exponentially. So what does it say? So essentially it says that suppose this is a distribution of Sn, right? We know that Sn would converge asymptotically to a normal distribution. This is bounding the probability of its tail. It's saying that this tail, the area under the curve, is very small. So how small is it? As you move a little bit away from it, it goes to 0 exponentially, actually doubly exponentially, so e to the power of minus t squared. Okay, and a slightly easier to use version, especially for computer scientists who want to state results such as with probability 1 minus delta, is the following, right? So if you just apply Hofstein's inequality to both x and minus x, and then divide this Sn by a factor of n, then you can work out that the mean converges to the expected value, and this is the square root of 1 over n from the central limit theorem that we've seen previously. when we say with probability 1 minus delta, we say that with probability at least 1 minus delta. So how do we check this? So basically plugging this expression into basically let's first divide this by n. So if t over n is equal to square root of b squared 2n log 2 over delta, then t is equal to n times b squared over 2 log 2 over delta. And we can substitute into this expression, right? We can substitute this into this expression, and then we're calculating this here. We get e to the power of minus 2 nb squared log 2 over delta over 2 divided by n times b squared. So notice that we are assuming the same bound for each individual x, right? So now like these got canceled out, these got canceled out, the 2 got canceled out, and we got e to the power of minus log 2 over delta. This is equal to delta over 2, right? So this is one side of the bound. If you also prove the other side of the bound, then you get another 2 over delta. Altogether, the area under the curve of these two sides, so that gives you delta in total, right? So therefore, with probability 1 minus delta, you have this. So this is like very easy to use. So remember this expression. So there's an improved version for the Hofding's inequality called Bernstein inequality, in which case we want to get something stronger when we have the variance calculation, when the variance is much smaller than b squared over 4, right? So this is also something that's nice for any random for any random variable satisfying that it is, say, between 0 and b, then the variance of this random variable is always smaller than 4 over b squared, right? So this is this is a variational result that applies to any bounded random variable. So sometimes when the variance is substantially smaller than such worst case bound, then we want to have the stronger inequalities that capture something that's more similar to central limit theorem. So remember, in central limit theorem, the right hand side is the variance rather than the boundedness, square of the boundedness. Okay, so Bernstein's inequality is just the same things, right? So we assume that the input random variables are independent, they are zero mean, but you can always convert any random variables that's not zero mean by subtracting its mean, right? So let's say you have y1 to yn, right, that are not zero mean. You can construct x1 to be y1 minus the expected value of y1, and then x will be zero mean, right? So that's how you apply this more generally. Basically now this depends on the variance of xi, right? So when the right hand side depends on the variance of xi with some algebra, which I will not show you here, but you should try work this out yourself. Then you can get the bound of the same easy to use interface that says is with probability at least 1 minus delta. Then the average converges to the mean with a bound of 1 over square root of n. Whereas inside the square root, you have the variance of x, right? In the IID, so x1, like it doesn't matter whether you do x1 or xk or x1000, they're all the same. And then the boundedness does still like enter the picture, but it enters through a term that's substantially smaller. So notice that so this is small o 1 over square root of n, right? This is big O 1 over square root of n, right? So the second term becomes negligible. So this is big O 1 over n. So as n gets larger, so it really depends only on the term that depends on the variance. So this is the same as that of CLT. Okay, so you should think about Bernstein's inequality as some kind of a finite sample type of result to calculate the convergence of the mean, without like making use of the more heavy-handed tools such as Bayesian, which shows the convergence of the CDF to the Gaussian distribution CDF, which is usually not needed in most cases. Okay, so we needed to define like one more concentration inequality that generalizes the Hofstad's inequality quite remarkably, even though it's a quite a simple generalization. So the McDiarmid inequality also deals with independent random variables, but now instead of just taking averages, we can work out the arbitrary Lipschitz function f. So let's first stare at this inequality. So this is still talking about the convergence of the random variable to its mean. And this random variable being the function of x1 to xn have a lot of independent randomnesses that are hidden inside this f, right? And then the expected value of f, so this converges to its expected value, and the McDiarmid inequality says that it converges to its mean value like very quickly as this epsilon gets larger, doubly exponentially as this epsilon gets larger. Now let's get to the condition for this to be true. So what this really requires is the some kind of replace one stability, right? So we need this function like for any input sequence f1 x1 to xn. If I replace one of them, if I just throw away one of the data point and add another data point in at the same location of that, then the perturbation of this f is always bounded by Ci. It's always bounded by Ci. So this is it depends on I. That's why I'm calling it a coordinate-wise stability condition, and it's a uniform stability condition because of this soup. Because of I'm taking all possible input to this f and requires this inequality to hold for all inputs. Okay, so why is this useful to us? So we are going to be taking this f to be the we're going to be taking this f of say p hat p to be the p hat minus p 1 more. So this is how we're going to be using this. And why is this the form of this f as a function of x1 to xn? So what are these x1 to xn here? So x1 is equal to the like we said, the indicator of whether whether s1 SA is equal to S prime. Okay, so this is our indicator, and we'll pad this. Yeah, actually, let's define this x1 to be the standard basis supported at S1 SA. So what is this? This is to say that you are 0 otherwise, but you are 1 at the location S1. Yeah, we get it. Yeah. So then why is this useful? P hat is equal to 1 over n sum over ESI SA. Right. So you can construct this. You can construct the estimator of the probability distribution by simply adding this indicator vector, right? And each individual vector is independently sampled, and we define this to be x1 to xn. So in this way we can apply McDiarmid inequality to somehow bound the concentration of this difference of the L1 norm in yeah, so sorry, let me patch this statement a little bit. So x1 is not quite this E of S1. So xi is equal to, because this one is not This one is not zero mean, and we want this to be the L1 norm of the difference, right? So let's define this to be indicate to be the standard basis at SI SA minus the probability distribution of probability distribution at SA, right? So that will be the XI. So notice that this is zero mean, and it is independent over the different I. Okay, so now that we have this construction, we can apply the McDiarmid inequality to obtain the obtain the bound. And I guess the only missing pieces is how large is this CI, right? So can we bound this CI as well? So this is relatively easy to bound because this is essentially the summation of 1 over n xi minus p 1 norm minus 1 over n summation of xi subtract xj add xj prime, right? So this is the only difference, minus p. And by triangular inequality, we can bound this by xj plus xj prime 1 norm, right? And this is smaller than 2. Okay, so we've established that for all j, this cj is smaller than 2. So now we can apply McDiarmid inequality to obtain the bound. So what is it that we are getting? So recall that we are McDiarmid gives us a high probability bound of x1 to xn minus expected value of fx1 to xn, right? So what is this f again? So this f is a p hat minus p, 1 norm, minus expected value of p hat minus p, 1 norm. Absolute value, we know that this one is smaller than, like if we use the same, so notice that this is identical to the form of a Hofstad's inequality, right? So we can apply the bound of the Hofstad's inequality and get 2 n c square. So this is the same as that the b square log 2 over delta. Okay, and then we can substitute this c to be 2, right? As we calculated just now, and then 2 times log 2 over delta. And this small n is basically assigned to the capital N. Okay, so I'm basically applying the McDiarmid inequality, which I showed you how to, but this doesn't quite solve our problem yet, right? Because we want this to be small, but what this is saying is that this is close to its mean. So it requires us to further calculate the expected value of this bound, right? So how do we go about that? So first of all, this is what we want, and now we have the McDiarmid inequalities result, which means that by triangular inequality, we can bound this by this plus the p hat minus p, right? So this is and this part we already have this bound. So it remains to bound the expectation. So how do we calculate the expectation? Okay, so how do we calculate the expectation of the 1 norm? So the idea is to first use the relationships of the norms that you've learned. So anything that's 1 norm is smaller than square root of the dimension of the 2 norm, right? Because this is a summation of the individual coordinates, and this is a summation, square root of the summation of the individual coordinate square. right? So in order to bound the L1 norm with L2 norm, then you have to incur a factor of square root of D. So that's what we're going to be doing. So what's D here? D is the size of the state space because this is a probability distribution defined on the state space. Well, so this gives us the square root of S, expected value of P hat minus P, 2 norm. Now let's apply let's apply Jensen's inequality or Cauchy-Schwarz in this case again by replacing this with e to the power of P, because the square root inside the expectation is something that I don't quite like. So I'm gonna further relax it and then put the square inside the expectation. And by Jensen's inequality, then I know that this is always okay, right? And now this is becomes S. I guess this is a summation of expected value of P hat of S prime, sum over S prime minus P S prime square. And it decomposes coordinate wise. But what is this? So notice that this is the expected value of P hat of S prime. So this is really just a variance. And we know that this P hat is a mean of the Bernoulli distribution, right? And the Bernoulli distribution has variance variance P1 minus P, right? So this is equal to square root of S sum over S prime. So P of S prime 1 minus P of S prime over N, right? Over N is because I'm getting N samples. So in total, this term is always smaller than 1. So essentially I'm adding up adding up over the S square, and this is a probability distribution, therefore you add up to 1. So in total, this gives us a bound of square root of S over N. Okay, so plugging this back to here, then we get an overall bound of N log 2 over delta over N plus, sorry, this is 2, plus square root of S over N. This is the final bound that we got. All right, so is everything okay here? So let me like jump out a little bit of the derivation and talk about Mac-Diarmid inequality. So Mac-Diarmid inequality is really powerful because it allows us to compute tight concentration bound for a very general family of functions. So in this case, we're taking this function to be one norm, to be L1 norm of the error. And well, notice that the dimensionality doesn't appear anywhere in this inequality. But the key trick of Mac-Diarmid inequality and for it to work is really not about bounding the concentration. So bounding the concentration is usually quite easy, right? As we've seen, bounding the concentration, bounding the concentration of this f of the independent randomness to its mean is usually easy by simply applying Mac-Diarmid inequality. The tricky issue is often how do you calculate the expectation in the first place, right? For that, sometimes you need to construct more and more delicate bounds to obtain the good dependence on all the right parameters. Yeah, but I hope this illustrates and how Mac-Diarmid inequality works, and you can generalize this to other problems that with a tricky concentration situation that you may run into. Okay, so another like very popular trick that's often used in machine learning and in statistics is so-called union bound. It goes with different names. This is also called Boole's inequality, where bool is a Boolean's bool, and well, it's also like known as a special case of the so-called Bonferroni adjustments. So Bonferroni inequality. So people from who's coming from the statistics department might know this better. So the idea is really simple. It's basically says that, and this is also how we typically use the union bound for. So suppose there are two events. So let's say that this is event 1, this is event 2, that they possibly they intersect, right? So event 1 is unlucky situation. So failure mode 1. This is a failure case 2. So both of them are bad events, and luckily they happen with small probabilities, right? So what the union bound is saying is that the union, so the area that's of the union is smaller than the area of them to add up. So P of E1 union of E2 is always smaller than P of E1 plus P of E2, right? So it's just a very straightforward identity that turns out to be very useful. So previously we've been talking about this bound hold with probability 1 minus delta, and that bound hold with probability 1 minus delta. What this is saying is that we can consider these individual events separately by constructing bounds of the probability of E1 and E2 by delta, and then at the end of the day, the total probability of failure is always bounded by delta 1 plus delta 2. And of course, by induction, you can generalize this to this more general statement of union bound with a countably infinite like number of events. Okay, so what we're gonna do, so notice that now that we have a high probability bound for a fixed pair of SA, and we are showing the concentration of P hat to P, now we need to apply union bound to all pairs of SA. Right? So what do we got? So just now we have that with probability 1 minus delta, P hat SA minus P SA1 norm is smaller than square root of 2n log 2 over delta plus S over n. Right, so this is our bound. This holds with probability delta. So in total for all SA, it holds with probability basically S times A times delta. What is nice about this is that it depends only logarithmically in 1 over delta. So we can replace delta tilde. We can define delta tilde to be SA delta, and then substitute delta tilde into this inequality first, and then we can essentially bound this 1 minus gamma square by 2 log 2 SA delta tilde square root of n plus S over n, right? So that gives us that gives us a desired bound. Okay, and how do we calculate epsilon? And for this to be smaller than epsilon, it suffices n to be larger than gamma 1 minus gamma square epsilon I guess this is to the fourth gamma square 2 log 2 SA over delta. It suffices for n to be larger than this quantity. Yeah, there's also plus yes. Yeah, with some numerical constant that multiply in front of it. So is this good? Like not really, right? Because it depends on S, right? It depends linearly on S. So let's maybe make use of this bound to calculate the overall sample complexity. So we call that yeah, let's copy this over. So this is 2 gamma square 1 minus gamma to the fourth epsilon square and log SA over delta plus S, right? So this is a sample complexity bound, and if we want n to be larger than this, it means that the computational complexity bound would be NSA plus S square A log will be that, right? And since A is large, since N is large, then there really isn't anything that we can do to further improve this beyond the S square A bound that we already got from the value iteration. Okay. The thing is that this is not the end of the story. So this is not saying that this algorithm doesn't work, but rather it says that this particular approach that we analyze this algorithm, even though it has some delicate things that we can learn from, doesn't really give us the satisfactory bound. Okay, so maybe we should just try again. So as an exercise, so I encourage you to try applying Hofstein's inequality coordinate-wise to every S prime, to try the other approaches of instead of using the McDiarmid inequality, use Hofstein's inequality or use Bernstein's inequality to see what you got, right? So this will be a very good exercise for you to get hold of how these inequality are used and what are the kind of expected results that you should get out of them. So Hofstein's inequality sometimes are not so tight, and that's when Bernstein's inequality becomes useful. And in this case, even the Bernstein's inequality doesn't give us exactly the same thing as a McDiarmid inequality and the expectation calculation. Yeah, so I'll leave this as an exercise for you, and then move on to the second attempt. Okay, so recall in the last lecture we talked about this like Q error amplification lemma, which says that if we have an arbitrary Q in R of SA, and we can define a policy to be the arg max of Q SA, right? Then this like if this Q is close to the optimal value function, then therefore the policy is also close to the close to being optimal. But there is a factor of 1/1 minus gamma amplification of the error, right? So this was a lemma that we proved in the last lecture. So now an idea of getting rid of the S dependence. The first idea of getting rid of the S dependence is, well, can we get rid of the Holder's inequality that ends up requiring us to bound the difference of the probability in terms of 1 norm? Okay, so then if we can bound this using an error term with high probability that's independent to S, if we can bound the I guess a Q hat function directly, then we can improve over the previous bound. Okay, the argument is actually quite simple. Okay, so let's see how it works. So by the way, if you read the textbook, so this part of the proof in the textbook is somewhat yeah, I don't quite understand how it worked there, but this is an alternative proof that's a lot simpler that will work okay. Okay, so let's stick to the notes and what I teach in the lectures. So let's try to establish this lemma, which says that we can bound the optimal value function. So this is the optimal value function of the true MDP. This is a optimal value function of the approximate MDP, and they each satisfy this Bellman optimality condition. Okay, so let's try to prove this. So recall that recall that they satisfy Bellman optimality condition, which says that if you apply the Bellman operator, then this is a fixed point, right? So similarly, Q hat pi is equal to tau hat, right? So this is a Bellman operator corresponding to the approximate MDP. Okay, so let's substitute this. So by I guess Q hat minus tau. Let's subtract and add this term in the middle. Tau hat q star minus tau hat q hat star. Okay, and now we can apply the simple triangular inequality by getting this out of the way, plus tau hat q star minus tau hat q hat star. But notice that, so this is an application of the Bellman optimality operator, which satisfies it is a gamma contraction, right? So we can bound this by gamma q hat minus q hat infinity. Okay, so how about this one? This one, we're gonna be just substituting the definition of the Bellman equation. Then we can add r plus gamma and transition v star, right? So this v star is a optimal value function for the true MDP minus r plus gamma p hat. Now this is p hat multiply with so notice that in the whatever Bellman optimality operator, you are always maximizing the columns by this q star function. So this will be the max a of q star s and a, right? So this will also give us v star, right? If we collect everything together and cancel the unnecessary items, so this r got canceled out. We got gamma p minus p hat multiply with v star infinity plus gamma q star minus q hat star infinity. So the remaining thing to do to establish this key lemma is to move this to the left-hand side. Right, so this is the same as the left-hand side. So if we move this to the left-hand side, then divide both sides by one minus gamma, and then extract out this gamma, then we get this inequality. Then we establish this inequality. Okay, I hope this like simple analysis is clear. So we are applying the Bellman optimal gamma contraction property, and here we're applying the definition of tau hat, which is a Bellman operator of the empirically observed MDP. Okay, so now we get to the key trick of further knocking out a factor of S here by applying this key lemma. Okay, so let's just stare at this. What is this? V star is something that's completely data independent, right? So we can in fact take the so again, p hat is equal to, if you still remember that, is equal to this indicator vector of Si, Sa, right? Yeah, so this L infinity over Sa, so let me just exclude this Sa because we're working on a pointwise. So p hat multiply with v star, p hat, one of the coordinate multiply with v star. So this is an inner product. This is simply the 1 over n sum of ESI transpose of v star, which is the same as just evaluating v star at Si. Right? So summation over I. Right, so this is why I'm getting this, and on the other hand, like this is just a fixed quantity. That's the expected value of we have. So instead of solving like a d-dimensional S-dimensional concentration with bounded L1 norm. With this inner product, taking this inner product to collapse it to one-dimensional, we managed to knock up a factor of S in the square root. And then like notice that this is expected value of that. This is expected value of that. And all we have to do is to apply the simple Hofstein's inequality, which shows that with probability 1 minus delta, the sum of V star Si Sa converges to its mean value. Okay, smaller than 2n log 1 b squared log 1 over 2 over delta. This 2 is due to union bound and the absolute value. And the remaining question to ask is, what is b here? What is b here? Notice that every individual segment is always a value function, and value function by the discounting factor is always smaller than 1 over 1 minus delta by the geometric series. Therefore, we can replace b with 1 minus gamma square root of log 2 over delta over 2n. And that's it. And once we have that, we can substitute it into this bound. So let's keep track of the power on this 1 minus gamma. So we have a square here. So we have a gamma over 1 minus gamma square for bounding the approximate value function, and together with the value function amplification, V star minus this is smaller than L infinity norm of Q star minus Q hat pi hat star and over 1 minus gamma. I think there's a factor of 2, and by this lemma here, then we can further bound it by remember there's a 1 minus gamma square, so multiply with this additional 1 minus gamma, we get 1 minus gamma cube, 2 times what we have at the bottom. So this is square root of 2n log 2 over delta. Right. So we forgot to take union bound over all this SA. So let's add that SA here into the logarithmic factor by this change of variable trick. So by declaring delta to be SA times delta, or alternatively allocate a little bit of budget of failure for every pair of SA. Right. So in total, so the failure probability is delta. So we have this bound with probability 1 minus delta. So even though we got a much worse dependence on this 1 minus gamma thing, but notice that we have gotten rid of the square root of S dependence in the bound. So in this case, if we calculate the corresponding epsilon, then we can get n. It suffices for n to be larger than n to be larger than 2 over 1 minus gamma to the 6. Yeah, I think maybe I'm missing 1 gamma on top. Log 2SA over delta epsilon square, right? So and the total number of the total number of oracle calls is n times SA plus n times SA log number of iterations for value iteration. Okay, so in this way we can improve the dependence on the dimension on the size of the state space without while suffering a little bit of worse dependence on epsilon and the worse dependence on the planning horizon. Okay, so that marks the end of today's lecture. So I just wanted to say that none of these derivations are optimal. So there's a lower bound that says that it requires this many samples for us to learn an epsilon optimal policy under the generative model setting. And well, there is also upper bound that matches this lower bound, which further improves over the bound that we derived by factor of the planning horizon, 1/1 minus 1/1 minus gamma. So some of the recent literature on this are insist for that, oh, this is the first time that this lower bound is achieved by getting by the way, the lower bound was a lot earlier, but the most recent upper bound that tightens up the sample complexity is in CIS4.0. And then later they used a very different algorithm called a variance reduced version of a value iteration method by first data splitting and going over each split separately while running the value iteration. Then the Agawa et al. They showed the same results for the model-based approach and with a slightly better dependence on epsilon. So this applies to epsilon larger than 1, but not quite getting to the full generality when epsilon is smaller than 1 minus gamma. So this was resolved in a more recent paper using a slightly different approach to either the model-based approach nor the value iteration-based approach. And my student Ming, he has a pair of work that has results that implies certain computational bound in this setting, which shows that for the finite horizon MDP case, you can get this optimal bound when epsilon is smaller than square root of h. So basically, you should consider h to be roughly 1/1 minus gamma in the infinite horizon case. And in addition, like for specific algorithms and not the model-based plugging approach, Ming also derived something that shows that for the full generality for the entire space of an arbitrary choice of epsilon, then you can get the sample complexity for both the infinite horizon case and finite horizon case. Okay, so remains an open question whether the pure model-based plugging approach is optimal for all epsilon smaller than 1/1 minus gamma. But these are still area of active research. Okay, so I'm gonna conclude, and in the next lecture we're gonna look at more reinforcement learning algorithms, and then we'll talk a little bit about some ideas on improving the dependence on 1/1 yeah, on the planning horizon. Yeah, thank you very much. The lecture video will be posted. Yeah, if you have any burning questions, feel free to ask now, or I'm happy to answer your questions on Piazza.
Thank you.